Hi everyone. So let us see more problems based on calculation of center of mass or center of gravity. So here you can see, find the CG of a cone of height h from the base. So if you take a cone and its height is suppose h. Okay. So we have a cone of height h from the base, and second we have to calculate a center of gravity or center of mass of a hemisphere of radius small r from its flat surface. So first let us consider the first part. So consider a disk of thickness dz at a distance of z from the vertex of the cone. So this is the vertex of the cone. From this at a distance of z. So let us consider somewhere here at a distance of z. Okay, at a distance of z from the vertex of the cone, thickness dz. So suppose you consider this thickness as dz. Okay. Then now if we compare, suppose A is the area of the disk and r is the radius of its base. So r is the radius of the base. H is the total height. We have considered this thickness of the disk dz at a distance of this z from the vertex. So we can have this proportionate relationship, z square upon h square is equal to a upon pi r square. A stands for the area, pi r square also area. So this side it is the area to area ratio, and this side it is your height to height ratio. H is the total height, so corresponding to that we will get this relation. Z is at a distance, this thickness is considered at a distance of z, so we have this z square. So we have considered left side the height ratio, right side the corresponding area ratio, so that we have z square upon h square is equal to a upon pi r square. Now from that we can consider the mass of the disk. A into dz, A is its cross sectional area, dz thickness, so this becomes the volume, rho density, so that gives you the mass. Replacing these values from here, we get this relation, pi r square upon h square rho z square dz. Now the center of mass or center gravity, that will be what? When it is a case of variable, so instead of addition like m1 x1 plus m2 x2 plus m3 x3 and so on, we will consider the integration. So this will vary from what? This 0 to this h. This z will vary from 0 to this h. So considering, and depending on that this thickness will vary. So considering that, we can consider, because this cross section we can consider here, 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 or anywhere we can consider throughout this cone. So this variation of this thickness, it will be from this 0 to h. If you take this coordinate as 0, so this coordinate here as far as the height is concerned, that will be h. So it is 0 to h. And m1 x1, so m1 x1, so this is considered at a distance of how much? Z. So m1 x1, so here it is z. Total mass, so total mass of the cone, that expression is known to us, so we can replace it by that, integrate it. This is a simple integration, z cube dz, so it will be z to the power 4 upon z, that z will be replaced by h, simplify, and you will get this relation. So from here we are getting this, but this will be from where? This will be from the vertex, but we are supposed to calculate it from the base. So this total height is h. This will be suppose h by 4. So this will be 3h by 4. This 3h by 4. So remaining, so from this side it is 3 by 4h. So from this side it will be how much? H minus 3 by 4h. So h minus 3 by 4h, that gives you h by r. So from here we can calculate the center of mass. It means of this cone, the center of mass is located at 1/4 of its height. So that we get from this calculation. Similarly, we can consider for the hemisphere. So if you consider this, So again consider a disk of thickness dz at a distance of z from the center along the axis. Radius of the disk, again it will be square root of r square minus z square. These are the standard geometrical relation that you can refer and you can consider this. So mass of the disk, again it will be pi r square dz into rho. So this part again gives you the volume into rho, that becomes the density, pi r square dz into this rho. So we are getting this expression. Again this will vary from what? 0 to this pi. So again integrating this and substituting the value of this mass m1 x1, again that relation, or you can say integration of dmx mx. So dmx from the lower limit to higher limit divided by the total m, calculating we will get this relation. So from here again after an integration we get 3 by 8 r. So it means the center of mass of this hemisphere, it will be at a distance of 3 by 8 r. So that way we can calculate it. Now the next question is, a solid of uniform density is made of a hemisphere. Again the nature is hemisphere and a right circular cone. So it is combination of right circular cone as well as the hemisphere, which have a common base of radius small r. Determine the value of h of the cone if the center of gravity of the system is at the center of the base. So already here center of gravity location is already given. So we have to calculate the value of this h. So again we can consider mass of the cone, that will be same 1 by 3 pi r square h rho. These things you can refer as a relation, geometrical relation. Now distance of its center of mass, it is h by 4. Okay, and the mass of the hemisphere, again from this geometrical relation, that will be 2 pi by 3 r cube rho, and let us say it is m2. Similarly r2, the distance of its center of mass 3r by 8. Okay, center of mass in general, the expression is m1 r1 plus m2 r2 upon m1 plus m2, but here the center of mass will be what? The coordinate is 0. That is already given because at the center of the base. So measuring the coordinate from the base, obviously its coordinate will be 0, and that's why it is taken as 0. Now again this equating the entire expression, this m1 r1 plus m2 r2 upon m1 plus m2. So this is center of mass, so it will be equated to what? This 0, because already that location is given. Equating it to 0, we are getting this h, which is coming as square root of 3r. So that way we can calculate it. Now you can see this problem. A particle of mass small m. Now this type of question, the previous question that was based on the geometry of the object. Now these problems are based on the conceptual part as far as the movement of the objects are concerned. So a particle of mass small m is placed upon the smooth face of a prism. So let us say this is the prism, this is part of the prism. Now a small m is lying over the face of the prism. This is the face of the prism, so here this small m is lying. Also of mass m, which is resting upon a smooth horizontal table. So this is resting upon a smooth horizontal table. The face of the prism on which the particle is placed is inclined at an angle of alpha to the horizontal. So this angle is alpha, that is also given. Prove that when the particle has moved a distance x, this object has moved a distance of x down the face of the prism, the prism itself will have moved a distance of half x cos alpha. So this we have to prove. It means this is the prism, it is lying on the surface or a table surface. A small m is lying, suppose somewhere here, this block. Now it has moved a distance of x on the face of this prism. There is no friction anywhere. So how far this prism will move? So that is the question. So here if we consider, let us say x1 is the distance of the particle along x-axis. x1 is the distance of the particle along x-axis. So we are taking this x-axis. So x1 is distance of the particle along this axis. Okay, beginning and x2 is the distance of the center of mass of the wedge. This is taken the particle along x-axis in the beginning, means before the motion starts. So coordinate or x coordinate of the particle, it is taken as x1, and x2 is the distance of the center of mass of the wedge. So center of mass of the system, it is at a distance of x2, and that particle is at a distance of x1 along the x-axis, means the x coordinate. So center of mass of this entire system, it will be how much? mx1 plus mx2 upon m plus m. But prism and this mass both are having the same value, so m and m, that's why here it is mx1 plus mx2 upon m1 plus m2, means m plus m. So that gives us x1 plus x2 by 2. Now x1 dash with the distance of the particle after m has moved a distance of x. After this m has moved a distance of x, its x coordinate is now x1 dash. Okay, and x coordinate of the wedge, it is x2 dash. That is now, so this was before the movement starts. Now this is assumed after the movement has happened. Now relative displacement of the particle on the right is x cos alpha, because if it has moved x along this direction, along the inclination, if it has moved x, so it's x, because this angle is alpha, so this component will be how much? X cos alpha. So that is x cos alpha. The displacement of the particle, the relative displacement, because the prism is also moving. It is not only that this object is moving, the prism is also, this wedge is also moving, and this particle is also moving. So relative to that, the displacement will be x cos alpha. Now since relative displacement of the particle relative to the wedge is equal to absolute displacement of the particle to the right and minus absolute displacement of the wedge to the right. The wedge is moving, the particle is also moving. So just comparing this, I am moving and suppose the surface is also moving. So I will have some kind of relative motion. So here relative displacement of the particle relative to the wedge, that is equal to absolute displacement of the particle to the right minus absolute. Relative displacement is what? Movement of one with respect to another. So movement of first particle, if it is suppose x1, of the second particle if it is x2, then the relative of first with respect to second, it becomes x1 minus x2. So that's what it is considered here. So the relative displacement of this, it is the absolute displacement of the particle, suppose x1 to the right minus the absolute displacement of the wedge to the right. So that is that concept of the relative displacement or the movement, it is considered here. So from this you can consider, so x cos alpha is the relative displacement, that will be equal to how much? x1 dash minus x1, because initially it was x1, finally it was x1 dash, its relative it will be x1 dash minus x1 of the wedge. This is of the particle. Of the wedge, again initially it was x2, finally it is x2 dash, so it is x2 dash minus x2. So we have this relation. Now so center of mass, so center of mass, it will be how much? mx1 dash plus mx2 dash upon 2m. This is just because masses are same, otherwise we would have been taken m1 x1 dash plus m2 x2 dash upon m1 plus this m2. So this is equal to how much? x1 plus x2 dash divided by 2. Now x centimeter, it should be same as x cm, it should be same as x dash cm, because there are no external forces acting on the system. So when there are no external forces acting on the system, it means there will be no shift in the position of the center of mass. So using that concept, we are considering the initial center of mass, it will remain same as the final center of mass coordinate. As far as coordinate is concerned, considering this, we will get this relation. Now x cos alpha minus x2 dash minus x2 minus x2 dash minus x2, that will be equal to how much? Minus of 2 x2 dash minus x2. These are just the numerical calculations. From here you can consider x2 dash minus x2, that is equal to minus of half cos alpha. So obviously it will be this minus this is minus sign, so x2 minus x2 that is will be the positive sign, so it is plus half cos alpha. So this is the final displacement which was supposed to be proved, that you can see here. So we were supposed to prove this one. So using that calculation we can consider this. I hope this is clear. So the concept which is used here is, when there are no external force acting on the system, there will be no shift in the position of the center of mass. Initially it remains same as the final location of the center of mass. So using that concept we are able to calculate this. Now see this question, two particles P and Q are initially at rest and 1 meter apart. So suppose there are two particles P and Q, they are at rest and separation between them is 1 meter. P has a mass of 1 kg, this is 1 kg, and Q a mass of 3 kg, so this is of 3 kg. P and Q attract each other with a constant force. So they have the force of attraction between them. At what distance from P original position, P's original position, do the particles collide? So if this is the original position of P, so with respect to this reference point or this reference line, at what distance they will collide? So that we have to calculate. Now here you can see, since the two particles move under the mutual attraction and are free from any external force, again we will use the same concept, that there will be no shift in the center of mass position. So their center of mass will remain stationary as they approach each other. Hence they will collide at their center of mass. So collision will happen at the center of mass when they come in contact with each other. So referring distances from P, this initial, we have 1 into 0, m1 x1 plus m2 x2. So taking this reference, its mass is 1 and its center of mass is located at its own location. So that separation will be how much? 0. So 1 into x1 means 1 into 0 plus m2 x2, so m2 is 3 and x2, this separation is given as how much? 1 meter. So from this reference point x2 is how much? 1 meter. So m2 x2, that is equal to how much? If x is the center of mass location, so that will be m1 plus m2 into x, because the entire mass of the system is supposed to be concentrated at the center of mass. So m1 plus m2 into this x. Simplifying this, you will get x equal to 3/4 or 0.75 meter. We have two particles here, m1 and m2. This is the reference point. This separation is suppose x. So here, if you calculate it with respect to this point, so its coordinate it will be 0. So m1 x1, so x1 is 0. So it is m1 x1 plus m2 x2. So this is x, or particularly here it was 1. Now they have collided and they are now at the common center of mass. So the total mass concentrated there, it will be how much? m1 plus m2, so 3 plus 1 into that x, because reference point is here, and from this reference point we have taken this distance as x. So from this we can, means the center of mass distance as x. So we have considered this. Simplifying, you will get this relation. Now next you can see a pulley fixed to the ceiling, So suppose this is the ceiling and there is a pulley fixed to it. Okay. A pulley fixed to the ceiling carries a thread with bodies of masses m1 and m2. So we have this pulley system, we have this m1 and m2. Attached at its end, the masses of the pulley and thread are negligible. Okay, and friction is nowhere. Find the acceleration of the center of mass of this system. So obviously when you consider this mass system attached with this pulley, so if m1 moves up, m2 will move down, or vice versa. If m2 moves up, then m1 will move down. So corresponding to that, there will be some acceleration of this system, so we need to calculate that acceleration. So that will be the acceleration of the system. The distance of the center of mass from the center of the pulley, from this, let us say it is axiom. So it is m1 x1 plus m2 x2 upon m1 plus m2. So where x1 is its distance from the center, x2 is its distance from the center of the pulley. So considering that, we have this relation. Similarly, after some time, it is now it has moved. So it is now at a distance of, suppose, x1 bar, and it is at a distance of x2 bar. Then the center of mass at that situation, it will be how much? m1 x1 bar plus m2 x2 bar upon m1 plus m2. But acceleration of m1 is equal and opposite to that of m2, because m1 and m2 are attached with the same string. So displacement of this, it will be same as displacement of this, because they are connected with the string. So they can't have different acceleration. Now when this moves up, so this will move down. Okay, that is the only thing, but displacement will remain same. Corresponding to that, the velocity will remain same, and corresponding to that, the acceleration will remain same, because all of these quantities are directly proportional to each other. So using this relation, can we say x1 double dot here? Double dot means d2 x1 upon dt2. The second order differentiation of x with respect to time t, that will give you the acceleration. Dx upon dt, that gives the velocity. d2x upon dt2, that gives you the acceleration. So just differentiating, we are getting m1 minus m2 upon m1 plus m2g. So x1 double dot is equal to minus of x2 double dot, because they are oppositely directed. One is moving up, then another is moving down. That's why we have this minus sign. So using this concept, we are getting this. So from here, x double dot cm means d2x upon dt2, d2x cm upon dt2. These dot here are for the representation. First order differentiation, we write x dot. Second order differentiation, we write x double dot. Third order, if you need to do, x triple dot, and so on. Similarly, you can also write x prime, x double prime, x triple prime, and so these are the various notation for the differentiation. So using that concept, we are getting this. So this is the acceleration, because it is the second order differentiation of displacement x or the center of mass. So from that, we get this acceleration of the center of mass of this entire system. Now see this question. A man weighing 60 kg is standing at the center of a boat. So this is the boat. Okay, and this man is standing here at the center of the boat. And he is 20 meters from the shore. So if this is the shore, so he is at a distance of 20 meters from this. So this distance is 20 meters. So he walks 8 meters on the boat towards the shore. So this side is the shore. So he moves 8 meters towards this. So he moves, this man moves this side. Okay, 8 meters. So this is given as 8 meters. Okay, from this to this position, he has shifted or moved. The boat weighs 200 kg. Mass of the boat, it is given as 200 kg. How far is he from the shore at the end of this time? Means when the man has moved a distance of 8 meters. So now you can say, why this question? He has already moved 8 meters. Initially he was at a distance of 20 meters. He has moved this side 8 meters. It means he may be at 12 meters, 20 minus 8, that is 12. But this will not happen, just because when he is moving this side, the boat is also moving this side. Okay, so 8 meters he has moved this side, the boat with the man has moved this side, so there will be some shift in this side. So we need to calculate that shift, and then accordingly we can find the final location of the man with respect to the shore. So that we have to calculate. So now you can see as the system is free from external force, the center of mass of the system again consisting man and boat must not move, and that will remain same. So let x be the distance of the man from the shore after he walks 8 meter on the boat. So when he has moved a distance of 8 meter, so finally his location from the shore is at a distance of x, because boat with the man has also moved this side. How much it has moved, that we don't know, and that's why in general we have considered this x. Okay. Now referring to all distances from the shore, we have 200 into x plus 8. 200 is the mass of the boat. So 200 into x plus 8. 8 it has moved this side, and x is what? X is its distance. So the boat center of mass, it will be how much? X plus that 8. So 200 into x plus 8 plus 60 into x. 60 is the mass of the man. X is the distance from the shore. Shore is taken as the reference point. So m1 x1 plus m2 x2. So 200 into x plus 8 plus 60x, it should be equal to how much? 260 into 20. 260 into 20, because the total mass of the, we have taken m1 plus m2 into x, m1 plus m2 into x. So total mass of the boat and the men, because once we calculate the center of mass of the system, it means the entire weight is supposed, or entire mass is supposed to be located at that point. So entire mass, that will be 200 plus 60, so it is 260. It is at a distance of how much? The center of mass of the system, 20 meter. So 260 into this 20. Simplifying this, you are getting x is equal to 13.8 meter. So that x is equal to 13.8 meter. So it means x is what? X is distance of the man from the shore after he walks 8 meter. So he has walked 8 meter this side. Initially already he was at a distance of 20 meter. It is expected that from shore, if the boat would not have moved, he would have been at a distance of 20 minus 8, 12 meter. But boat does not remain at rest. Boat has also moved this side. So it means some distance it has moved. So here, if from this, if you can calculate, so boat has moved how much? 1.8 meter, because he would have been at a distance of 20 minus 8, that is 12, but he is at a distance of 13.8. It means the boat has also moved at a distance of 1.8 meter. So this is the final location of the men from the shore. I hope this is clear. So this way, using the concept of the center of mass, and particularly the main concept that we were using here is, if there is summation of all external force acting on the system, it is 0, there will be no shift in the position of center of mass. Using this calculation, we have calculated some of the problems which could have been calculated in a very difficult way if we would have used some other method of motion, whether it is one-dimensional, two-dimensional, or the concept of relative velocity. So this gives you a simple calculation if you use the center of mass concept. Thank you.